Hello, my name is Nikita, and we will talk about fast and hopefully efficient network protocols in Rust. But before we dive into that, a few words of introduction. I worked on a couple of databases before. I worked on MongoDB, ClickHouse, and Yandex database. My specialties are system programming and query engines, and I'm especially in love with Rust. Before we sort of dive into the distributed systems part, let's talk about the motivation first. And for that, I would like to present Elfo. Elfo is a Rust framework for actor programming. As I'm sure a lot of you already know, actor programming is a model for concurrency. It's a model where you can spawn a lot of single-threaded tasks, and the only way for them to exchange data is to send messages. So there are no mutexes, no locks, no atomics. The only way to send data between threads is through messaging. That maps really well to Rust and its asynchronous tasks. So that's why we developed Elfo. Apart from the obvious thing, which is the message passing, Elfo implements a bunch of our features as well, such as routing. You can, in the runtime, decide which actor receives a particular message, depending on some conditions. It also provides Erlang-style actor restarts to make sure that even if you encounter the bug or some unrecoverable condition, your actor will restart and your service will continue to serve requests or whatever it is serving, and much more. So Elfo is a fully featured framework for building services on top of actor programming model. To give you sort of the idea of how working with Elfo looks, let's write a very simple actor that sends a message of just one field. So here we first define the message, and all messages in Elfo are just Rust structs. So you define the Rust struct as usual. This could also be an enum. You can also have like some nested fields there. So use structs as usual and slap an procedural macro on top of it called message to make this struct sendable. And then, as I said before, actors in Elfo are just async tasks. So you define an async function that represents your actor, and you can use the context to interact with Elfo in some ways. For example, sending a message. You just construct a greeting message, pass some data to it, and asynchronously send it. So this all works really well on a single node, and that's actually how Elfo started. Elfo started with just single node deployments and a lot of actors inside that single node. As you probably already guessed, when we are on a single node, we can use existing Rust abstractions to do message passing. One of such abstractions which works really well is channels. So basically, each actor has a channel inside of it, which we call a mailbox. And every time we want to send a message to an actor, we put a message inside the mailbox, and then actor can receive a message from this mailbox. And that's how it works. So very simple idea, but very flexible, and it served Elfo really well. Unfortunately, we do not have an abstraction like that in a distributed environment. So if we have two actors on a completely different nodes, there is no channel between them. There is no abstraction like that in memory or in some other form. Of course, there is network, but network is wildly different. So how do we provide actors with an ability to send messages between nodes using the same interface? And when we're talking about remote calls and sending messages over the network, the first question which pops into the mind is, why not use existing solution? So I will talk about gRPC. There are many other protocols, many other APCs out there with very similar properties. So a lot of arguments I will mention will apply to other protocols as well. So as you probably already know, gRPC is RPC protocol based on protobufs. So you define messages or, whatever you want to call them, messages, structs, you define them in protobuf, and you can define also the public interface of your server, and people can call certain methods on this server by using protobufs. So this sounds a lot, at least from first glance, a lot like Elfo, so why not just use it? There are a couple of problems here. First problem is the serialization format clock-in. So as I said, the gRPC strictly uses only protobuf, and it might seem okay for a lot of cases, and it actually is. Protobuf, at least for its time, was a revolutionary format, I think. And it works really well in the context of Google, but unfortunately, protobuf has made some decisions which we do not really agree with. Elfo was designed initially as a framework for building a high-frequency trading system, so latency is really important for us. Protobuf is not very low latency format in the sense that it offloads quite a lot of work for you to do in the CPU during deserialization. One example of that is how protobuf encodes integers. Integers use varint format, which is quite CPU expensive to decode. And we just wanted more freedom than that. We wanted to experiment with a couple of formats, maybe use different formats depending on what kind of deployment we have. And gRPC does not allow us to do so. Then, sort of like the elephant in the room, RPC is a subset of message passing. You can emulate message passing on top of RPC, but that's just the thing. It's emulation. It's not actually message passing. This kind of leads to the next point, where some Elfo concepts don't really map well to gRPC. So we can emulate messages, but Elfo messaging system is actually very expressive. It already supports requests, so this is your typical HTTP-like send a piece of data, get a piece of data back. It soon will support subscriptions as well, and for each of these types of messages, we need to do some tricky things with gRPC to again emulate that. So while we could use gRPC, it would not look. We would go through quite a bit of hurdles, and when you use an abstraction and it requires you to get through these hurdles, maybe you need to take a step back and rethink how you approach the problem, and that's exactly what we did. So we kind of invented our own gRPC. Again, this is not actually what happened, because our system has different guarantees and different structure to gRPC, but that's what we went with. Before we go into the gnarly details about how message encoding works, how do we do message compression, let's talk about how we structure connections. So you would probably expect that, like in a typical server, you will have one connection between the two nodes and send all the data between them. In Elfo, we make use of multiple connections. So when two servers want to connect to each other through the discovery mechanism, this is to say that they have their IP addresses in their configs, so they want to connect to each other. They first establish a control connection. So all connections here are normal TCP connections, but they have different roles. So control has two roles. First is the handshake, and second is sending some metadata. We'll talk about metadata a bit later in the talk. So let's discuss handshake first. So we need to ensure that our system works even when some nodes use older version of the code than others. So, for example, we do a rolling update, and we only have updated half of our servers, and for some reason we stopped the update process, maybe something went down, or maybe we just went on a coffee break. We do not want our system to be broken in this state. To ensure that the control connection, when the initial handshake happens, each node tells the other what is the set of features it is able to use. For example, maybe we implemented a new compression algorithm like ZSTD or something like that, and the other node does not support it. If we start sending ZSTD data to the other node, then something will break. So this initial handshake phase ensures that that both nodes talk on the same language, using the same protocols and same features. And the metadata stuff we'll cover a bit later. And now to the sort of load-bearing connections of the whole system are so-called data connections. So you can see these actors here are organized in actor groups. This is a logical organization. It doesn't really affect in any way how do we interact, how do we map actors to different tasks or anything like that. So this is a logical grouping to make reasoning a bit easier. For example, if you have a bunch of actors, each of them serving a WebSocket connection, they can be grouped into the one big WebSocket group. Again, makes reasoning a bit easier. And it also allows us to do some grouping to establish less connections between nodes. So each each pair of actor groups which would like to talk to each other establish a data connection, and this is where we actually send all the messages. So metadata on the control connection, the message data on the data connection. So how do we actually encode messages in our system? How do we, what do we actually send over the wire on the data connection? We use a codec, in-house codec, which encodes each message as an envelope. Envelope has two parts. First one is header, which contains some meta information useful for the system and potentially useful for the user as well. So we have size, flags, kind of message, all this kind of stuff. This is internal Elfo information. We also have a sender and a recipient in the header. So each actor in Elfo has an address. So the sender field tells us what is the address of the actor which sent the message, and the recipient tells us what's the address of the actor which receives the message. So it is actually quite useful for the receiving end to know this information, because if they want to send a reply directly to the actor which sent the message in the first place, they can use this field to reply. We also have a request ID, which is an internal Elfo stuff, and we have a trace ID because Elfo supports observability out of the box, and trace ID allows you to basically mark a bunch of messages as having some logical connection between each other. For example, maybe there is a user request to do something that results in multiple messages being sent in the system. As long as they all have the same trace ID, you can then later group them and see what kind of ripple effect the request from the user had on your system. Finally, we have the message part, which actually contains the serialized message payload and protocol name as well as message name. So you can think of protocol name and message name as similar concepts from protobuf. So protocol name kind of tells you like what crate this message is from, and the message name tells you the name of the Rust struct, basically. And finally, the message payload contains the serialized data. So we actually do a couple of tricks when we're doing encoding and decoding of these messages, which I want to cover a little bit. I think that encoding is pretty, well, it's actually not, but you can imagine it as a pretty simple process of just getting the structs and calling, I don't know, serd, serialize or something like that. That's because we, on the sending side, we know what type of message that is. But how do we get back how do we decode the bytes into the Rust structs back? So here you have this decode function on the very bottom of the listing, which actually accepts this input as a list of bytes and some other arguments which are not relevant and returns the decode state. Decode state is an interesting enum because it has probably the three variants you expected, but each of them plays nicely with other parts of the system. So first one is the needs more data variant. So the message codec implementation and the actual I/O of the system are decoupled. They're in different places. So we need to somehow tell the I/O system that, hey, this message is incomplete, I need more data. And this is exactly what this variant is for. So every time the decode function sees that we only have half of the message, or there's just like even the header is incomplete for some reason, it says that I need more data, and it provides a length estimate. So the I/O layer knows that unless it reads at least this number of bytes, do not go back to the decode stage because we'll just return need more data again. Second option is skipped, and this is a bit unusual for an RPC system because it allows us to recoverably fail on message parsing. So if, again, for some reason we update our cluster and only half of the nodes in the cluster know the updated message types, and the other, another half of the system doesn't, we want to make sure that this whole cluster does not just fail, because it is very common for systems to try to decode a message from the network. If it doesn't If it doesn't match the schema which was defined beforehand, then we just kill the connection, exit, abort, and say that, hey, this is unrecoverable error. In Elfo, actually, if you, for example, made a mistake of adding a required field in the message, and the decoding pipeline failed to, well, decode this message, we will skip only this message and we'll continue working because other messages might be valid. So this is, again, a little bit of built-in resilience in Elfo to ensure that human mistakes do not result in huge production mistakes. Finally, we have a done variant, which is, again, probably what you expect. We have a decoded message here, but there is a catch. So the network envelope is a struct which essentially boils down to a pointer within any. This means that at some point during the decoding process, we were able to take the bytes and transform them into a Rust struct. But all the usual SERDI mechanisms require for you to pass a type. All the SERDI functions usually have a generic pass to them, so that SERDI knows exactly what type we are decoding. But you might notice that there is no generic in the decode function. And there can't be, because we cannot just list all possible message types in the generic argument for the decode function. So how does it know which Rust, how does it get the type of the Rust struct which we need to decode from the bytes buffer? And the answer is virtual tables. So remember this procedural macros message, which we discussed in the beginning. One of the things which it does is that it generates message virtual table. So every time you define a message, we generate an entry of the following struct. So we have a name and a protocol, which, if you remember, we've seen before in the message codec, which basically tell you which crate this message is from and what's the name of a struct. And then finally, we have a pointer to a function. This function can take the bytes inside. It knows which particular type it belongs to. It can construct this type, downcast it, upcast it to any, and return to the user. So this is the machinery which takes protocol name, struct name, and a bunch of bytes, and it creates an actual Rust struct. So in practice, we use a link me crate to collect all the virtual tables from the whole binary into one list. And every time we need to decode it, we look through this list, find a message with matching protocol and name, and call this function. Once we've done with all this encoding, decoding stuff, we need to handle the message compression as well. So message compression is presented in Elfo for cases when we want to make sure that every time we send a bunch of bytes over the network, we get as much value as possible. For example, especially in the trading scenario, it's quite common to have servers in completely different geographical locations. You might have one server in Asia, one server in the US, one server in Germany. And it is sending data between these locations has quite high latency. If we send 100 bytes, we want to make sure that we pack as much information into these 100 bytes as possible. We use LZ4 algorithm because it has a decent compression ratio and also has a relatively small latency. But no matter which algorithm we use, there is a balance between compression ratio and latency. Because ideally, for any compression ratio, any compression algorithm, LZ4 included, we want to accumulate as much data as possible before actually compressing and sending them. But accumulating data means that we add additional artificial latency on top of our messages. So message A, message B, message C are just waiting in the buffer for better compression ratio, but adding valuable milliseconds. So right now we use a very simple threshold approach where we accumulate a certain number of bytes, or rather kilobytes, of data, then compress and send them. But in the future, we might implement a more dynamic strategy to reduce latency even more. Yeah. The final problem Elfo tries to solve out of the box is so-called overwhelmed actors. So it is entirely possible for actors, even within the same node, but especially on different nodes, to have very different speed of processing. So in this example, we have an actor A, which sends 200 messages per second, but it doesn't know that the actor B can only handle 50 per second. So we, first of all, waste network bandwidth, but we also build an infinite queue on the receiving side. So this will result in either more stalls or out-of-memory error on the receiving side. One way to handle it is to steal from TCP and implement flow control. So TCP kind of does the same thing, so we got inspired and did it on top of TCP once again. We have so-called windows, which ensure that the windows ensure that we do not send more messages than the receiving actor can handle. In this example, actor B has a window of 100, so this means you can send 100 messages before you wait for the acknowledgement. So actor A does just that, sends 100 messages. Now the actor B window is 0, and the sending side cannot send any more data. The window is closed. You need to wait for the acknowledgement from the receiving side. So we wait for some amount of time, and then we use the control connection, which we mentioned in the beginning, to notify the receiving side, to notify the sending side that, hey, actor B has managed to process 100 messages. You can restore the window and send more data. So as a conclusion, we already had a robust API for sending messages and communicating between different actors on the same node. We now have the same API for remote messaging as well. So Elfo transformed from being an actor programming framework for a single node into a toolkit for building distributed systems at scale. We have a configurable message compression for cases when you need it. We have automatic flow control to make sure that the actors do not get overwhelmed, and to make sure that we use the network bandwidth efficiently. And we have observability included, so everything discussed before has a lot of metrics, which you can build nice dashboards of, and most importantly, debug production problems. Thank you.